Say supposing we are given this network which is there over here. This network that is given, this is an entire network consisting of connection of resistors of values 2R and R. This is the way the network is connected. This is 2R, this is R, 2R, R, 2R and 2R. For this network, you want to find what is the effective impedance across these arrow lines. So ultimately, what is the effect experienced at these 2 points because of this entire network? So now let us find out what is the impedance of this entire network experienced at these 2 points when I'm given a R and a 2R network. Okay. So if you want to find the effective impedance on this side, you have to start solving the network from this end. So what I encounter is, first this is this 2R and this 2R, okay. This end is connected to ground and this end is connected to ground. So this point is same as this point. This point and this point is the same, they are connected to ground. So what happens is these two become in parallel. So when both of them are in parallel, 2R in parallel with 2R, okay, how do you multiply? 2R multiplied by 2R divided by 2R plus 2R. When I use the parallel formula, get the equivalent resistance. 2R times 2R comes out to be 4R square. Denominator 2R plus 2R comes out to be 4R. This 4 and 4 gets cancelled, 1R and 1R get cancelled, so it is R. So what is happening is, when I start finding my equivalent resistance from this end, I know that these two are in parallel because this point is common and this is ground and this is ground, this is also common, so both these and this are parallel. So when I find parallel equivalent, I find that the value comes out to be of R. So what I will do is, this entire network which is there, I will replace it by a single resistor R. Okay, I'm now removing it and I'm replacing it with a single resistor R. One end is at this point, the other end is grounded. Okay, so those two parallel resistors get reduced to one resistor R. Now if you notice, okay, this resistor R and this resistor R, both of them are getting connected in series. So this entire network I have to again replace it at this point and this point over here. So let me eliminate one resistor because only this has to be replaced by 2R, as both are in series. This becomes 2R. Fine. Now the next network is across this point. Okay, this is ground and this is ground. So what is happening is, these two are connected again in parallel. So this is a common point, this is ground, is a common point. So again what is coming, 2R and 2R is parallel. So you have to find the parallel equivalent of this, and you know that the parallel equivalent of 2R multiplied by 2R parallel with 2R is R. So this entire setup, I have to replace it by a single resistor R. So I will eliminate this. And I will put a single resistor. Okay, sorry. So the single resistor R. Now what do you see, that these two resistors are again connected in series. So I have to replace it by parallel equivalent, okay, of 2R. Okay, the thing got eliminated, so I will just redraw it. This is actually a 2R, this doesn't affect. but this R becomes now 2R as both of them are series. And ultimately what will happen is this final network, if you observe, at this point is one common point for this resistor and the second point is a ground point. So 2R and 2R are in parallel, which turns out to be R. So ultimately it comes out to be the entire network that I have shown before. It can be reduced to a single resistor value R between these 2 points. So what I meant by this, that entire network which are shown to you, its effect at this point is equivalent to a single resistor of the value R. So this is an important concept. When I have an R to R network, okay, connected in the same fashion as shown, it can be replaced by a single resistor whose values are at this particular points. Okay, now we are given this above network. Okay, this above network is given to you for when the bits are 3. So bits are assigned the variable n and the number of bits is 3. So when I have 3 bits, the number of possible combinations are 2 raised to 3. 2. Why 2? It is because either each bit can take a value of 0 or it can take a value of 1. So for 2 bits, for 1 bit which can take a value of 0 or 1, 2 raised to the power of 3, we have 3 combination, comes out to be as 8. Okay, 8 possible combinations are there, out of which the first combination is 0, 0, 1. So the bit on my leftmost side, I call it as LSB. Sorry, on the rightmost side is called as LSB. The bit on my leftmost side, I call it as MSB. We start from LSB, we call it as B0, B1 and B2. So when I have 3 bits where each bit can take a value of either 0 and 1, the network, okay, for each bit would be 2R and R in combination, first bit. Second bit again 2R and R, and the last bit over here will take 2R and 2R. So for your last bit, always it will be 2R. For the remaining bits, it will be R and 2R combination. Okay? Now, so what you have to do is, this is my network that is given to you. So if n is equal to 3, you will have 3 networks like this. The last network will have 2R and 2R in combination. Okay? Remaining will have R and 2R. Now what is the first combination of these 3 bits given as 0, 0 and 1? So what is happening is, this n is taken as my MSB, okay, and this point is taken as my LSB. Now if you check, your LSB is connected to given a value of 1. So the voltage over here should be, when I say 1, it should be a reference voltage which is 5 volts. The second bit, this is B1. Since it is 0, you have to ground it. The MSB bit is again 0, so this is your MSB bit, so you have to ground it. Okay? Only your LSB over here is given as a reference. So now this value that you get depends upon the combination. The first combination out of the 8 that you taken is 0, 0, 1. Then there are 8 possible combinations. First let us understand how to work it out for this combination. Once you get the idea for one combination, the procedure remains the same for the remaining combinations. Now what you have to do is, for this first combination of 0, 0, 1, at this point over here, you only have to find what is the effective voltage, which I call it as VTH, and effective resistance, which I call it as RTH. So basically, what is VTH and what is RTH? VTH is a voltage at this point experienced because of this entire network. RTH is the resistance experienced at this point because of this entire network. Okay, with this as my input, 0, 0, 1 as my input. So now how to find my VTH at these particular points and how to find my RTH at this particular points. Now, to find RTH, okay, for this entire network, what you will have to do is, you will have to start solving this. Okay, when you start solving this, what will happen is, okay, finding this RTH, you will have to start solving this. Now this same network I will redraw it over here. It's 2R, 2R, R. This is 2R, this is 2R, R, this is 2R, this is R, and this is 2R. Okay. Now, this point, MSB point, is already grounded. B1 also is grounded. Okay. This is B0, B1, and the MSB bit. What you do to the MSB bit is, since you want to find your RTH across these points, whenever you find the effective resistance, you have to short the voltage sources. So this Vref is there, it has to be shorted, so you have to ground it right now. This 2R also is grounded. Here also actually it is grounded. Okay. Now, what do you do is, Vref, you have to make it equal to 0 when finding RTH. Now this network, what is there, is similar to the network that I have already discussed. That is, to find my effective resistance between these 2 points RTH, which I have actually explained in the first 5 minutes of the video. The procedure remains the same. So ultimately this circuit, okay, comes out to be the same as the first circuit that I explained. You will ultimately get the effective resistance at these points. RTH will come out to be R. So the purpose of explaining the first circuit, that is a combination of this R and 2R network, to find the effective resistance at these 2 points, is that same concept is to be applied over here. And the procedure will remain the same, and the answer also will come out to be the same. So actually the basic concept is, if you use any 2R and R network like this, combinations, okay, then the effective resistance will always be R. So your RTH over here comes out to be R. You can try it again, the answer will definitely be R. So your RTH is already sorted, as I already explained. Next, let us go to VTH. To find VTH, okay, this is my same original network. You know that your MSB is connected to Vref. Bit 1 is grounded and bit 0 also is grounded. So your job now is to find what is the voltage experienced at this points because of this network when I give a combination of 0, 0, 1 at these 3 input points. So how to analyze the circuit is, you have to find a VTH across this point, so you have to start solving the circuit from the other side. Now when you start solving the circuit on the other side, first you have to take this encircle network and find the effective voltage given by this network at this point with respect to this point. Okay. So how to find that is, if you notice, this resistor is 2R, this resistor is 2R, it is grounded. Here the voltage is Vref. So what is happening is, if I just redraw it, this is 2R, this is 2R, this is the ground, this is Vref, okay. this node, let me call it as A. This is my node A. So this network is like a voltage divider network. So how will I get the voltage at point A? It is Vref into 2R upon 2R plus 2R. Okay. So which comes out to be Vref into 2R divided by 4R. So when I cancel R and R cancels, this comes out to be Vref by 2. Okay. So the voltage experienced at point A is Vref by 2. And that's not the only thing. You have to replace this circuit. Okay. You have to actually, what you have to do is, you have to Thevenize this portion encircled in black. So when I Thevenize, in my Thevenin's equivalent circuit, what I need a VTH to replace entire circuit, and I need an RTH. Okay. VTH you already found out as Vref by 2 to replace this entire network. How to find RTH? To find RTH, what we will have to do is, this Vref will have to be grounded. So what that circuit will come out to be is 2R. This point is already grounded. The second 2R which is there, this is point A. Here where Vref was there, you have to now ground it, because you have to find the effective resistance at this point A with respect to ground. So what will happen is, if you notice, this 2R and this 2R are actually in parallel for this point, and this is my ground point. So both are parallel. So 2R in parallel with 2R will come out to be R. So this entire network, okay, I have Thevenized it and I want to replace it. And when I find my Thevenin's equivalent circuit, VTH comes out to be Vref by 2, RTH comes out to be R. So this entire thing now I will replace by a single voltage source and a single resistance, and I will redraw it. So what I have done is, this network which I was Thevenizing, I have removed it at this point and I have replaced it by a single resistor R, which is your Thevenin's resistance, and a voltage source over here. And what is that voltage source coming out to be? You calculated it as Vref by 2. Okay. So connect that in the form of the battery over here. Okay. So this is my Thevenin's equivalent circuit. Now what do you do is, the next network that you have to find out is, you come over here, okay, started with the yellow line. At this point, you have to again find out what is VTH and what is RTH. So you have to Thevenize now this portion of my circuit that I encircled in yellow. Okay. So I am going to Thevenize and I am going to find out what is the effective voltage at this point, okay, and the effective resistance between these 2 points. So if I notice, first of all, this R and this are in series. So what I will do is, I will replace them by a single resistor whose value will be 2R. And then I have to find out what is the effective voltage across this. Now to find my RTH, what will happen is, to find my RTH for this particular network, this Vref will have to be set to 0. So what we will get it as, this will be 2R, this will be 2R, this Vref we are setting it to 0, this is ground. So what is happening, 2R and 2R in parallel will give you R. So the effective resistance RTH over here is actually R. So this network, you have to actually replace it by a voltage source and a resistance, which is VTH and RTH, using the Thevenin's theorem to Thevenize this part of my network, where RTH is found out to be as R. Now how to find VTH, that we will see next. I will erase this part. Okay. We know that our RTH is R. Okay, I'll write it down over RTH is R. Now next to find VTH. So I will redraw my circuit. To find VTH, I have to get my voltage back. This is 2R, this is 2R, and this point is grounded. This is 2R and 2R. This point I will call it as point B. Okay. So you want the voltage at point B. So this is now again like a voltage divider network, where you have this voltage being applied across the series combination of 2R and 2R. So using my voltage divide rule, what I will get is Vref by 2, okay, multiplied by 2R divided by 2R plus 2R, because this voltage Vref by 2 is being applied across the series combination of 2R and 2R. So when I solve this, what I will get is, okay, this 2 and this 2 will get cancelled. So I can rewrite it as Vref times R. In the denominator it comes out to be 4R. Here R and R will get cancelled. So the voltage comes out to be as Vref at 4. So the voltage experienced at this point, VTH, is actually Vref by 4, and the resistance RTH is R. So now this entire network that is encircled in yellow will have to be replaced by a voltage source whose value will be Vref by 4, and a resistance whose value will be R. So let me replace over here. Okay, I will clean this part. This part also I will eliminate, just to show you all. Now what will happen is, this is my R, which is my voltage, and my Vref by 4. Okay, so that network I have already replaced it, whose equivalent I have already found out. Okay, so this is my final network. Now ultimately you have to find your final VTH experienced at this point, which is a final, okay, voltage at this point, which is a final VTH and a final RTH. So how to go about that again? To find your RTH, you will have to make this fellow to 0 and redraw my circuit. This will come out to be R, this is R, and this is 2R. Ground this, removing the voltage source means grounding this. This R and R can be written as 2R, this is 2R, both are grounded, and both of them are in parallel, which can be written as an equivalent resistance of R. So the resistance experienced at these points, okay, is R. So RTH will come out to be as R. Now we will find VTH. Okay, now how to find VTH? Okay, I will erase this so that it won't get confused. Now we have to find the VTH. To find your VTH, okay, what is this? I am having my Vref over here, Vref by 4. This is a series combination, 2R. I want the voltage at this point, C. Okay, so this is again my 2R, it is grounded, my point C is over here. So this again forms my voltage divider network. So I did as Vref by 4 multiplied by 2R divided by 2R plus 2R. This comes out to be half. Okay, this is Vref times R times 2, you divide and you multiply 1 by 4R. Okay, so you get cancel this, this comes out to be Vref by 8. So what is the voltage VTH in this case over here? It is Vref by 8. Fine. So what you do is, now this network, you wanted to find a VTH and RTH across this point. What you do is, you replace this entire network. Let me just erase this. Okay. This entire network, now I'm going to erase it and replace it by a single voltage source of Vref by 8 and the resistance of R. Okay. So now what I want to tell you is, ultimately the network that was given is combination of R into R. The effective resistance at the end will always be R. So that is your first 5 minutes video that I have explained. And again, when I repeat the procedure over here, the resistance remains R. Okay. What we have to find is, we have to find the effective voltage, which comes out to be Vref by 8. So what is happening over here? For the combination of V2, V1 and V0, where what was it, the value given to be as? The value was given to be as 0, 0, 1. When you give for 3 bits, this combination of 0, 0, 1, the voltage, effective voltage comes out to be Vref by 8, okay, and the effective resistance comes out to be R. Okay, so this is what you ultimately want. Now, something else to add to this is, I can make a table over here. Okay, I will erase this. What I know is, I'm having 3 bits where each bit can be either a 0 or 1. So the possible combination of 3 bits where each bit can be 0 and 1 is 2 raised to 8. So let us look at the combinations of V2, V1 and V0. Okay. First will be 0, 0, 0. Then you have 0, 0, 1. Then you have 0, 1, 0. You have 0, 1, 1. Then you have 1, 0, 0. 1, 0, 1. 1, 1, 0. And 1, 1, 1. So what are you having actually over here is, you are having 3 bits, okay, where each bit can have a value of 0, 1. So the possible combinations are 3, 6, 7 and 8. Okay, 8 possible combinations. So this will be the inputs that you will be giving to that ladder network which I have drawn. And what was that ladder network? This is my ladder network. Okay, these are my points. I will draw it with a different color. This is my LSP, V0, V1 and V2. Okay. Fine. This is 2R, 2R. This is R and 2R. This is R and 2R. This point will always be grounded. Okay. This point, okay, when marked as black dots, what marked as black dots are these inputs that are going to give. When the bit is 0, so for example, look at the first combination, V2 is 0, means this point is to be grounded. Now here all 3 are 0, so all these 3 points are to be grounded. If you look at the last combination, all 3 are 1, so all these 3 are to be connected to Vrefs. So when the bit is 0, meaning you grounded, okay, 0 meaning ground, and one meaning to connect it to a reference voltage, which is usually 5 volts. Here you ground, so it is 0 volts. Now like that, there are 8 possible inputs that you can give over here, and what you do is, at these points, okay, which are marked in X and Y, you have to find the effective voltage, okay, which is my final VH, and your effective resistance RTH. One thing that I will make it clear to you all is, this RTH will always be R, okay, irrespective of the inputs that you give from this range, irrespective of the 8 inputs that you are giving, this RTH is always going to be R. That's the effect of this entire network experienced at points X and Y will always be R. That is the same as what I have explained in the video from 0 to 5 minutes. That's why I took the time. Only what will change is VTH, okay, and that will depend, VTH, the voltage experienced at X and Y, because of this entire network over here, okay. And why this voltage is changed? Because you are changing these inputs, these 8 inputs that are given. You are changing these inputs which are there, okay. And because of that, your effective voltage of this entire network experienced at points X and Y will also change. So you all can try for 100, your VTH comes out to be Vref by 4, okay. For 001 I will explain, 100 it's Vref by, for 100 it's Vref by 2. Okay, and for 001 it is Vref by 8. For 010 it is Vref by 4. Okay, this you can calculate. RTH will be R, which will always be the same. I have already explained to you all how to do it for 001, it's already done. Now you can repeat the procedure for 010, VTH will be Vref by 4. It is a voltage experienced at points X and Y. When you calculate it, you let it as Vref by 4, where the combination is 0, 1, 0. So here you give ground. For 1 you give B1, you give 5 volts. For B2, which is MSB, again you are grounding. Same way for 100 combination, your B2 is going to be given Vref, okay, 5 volts, and B1 and B0 are going to be grounded. So for like that, you have to calculate what is the effective voltage VTH across my points X and Y for these various combinations of inputs. I have shown you for one, for the remaining two I have given the values. I will advise you to solve it and find out those values. Because based on this, once you understand how to get this voltage at these points, this network is going to be applied somewhere else. You have to understand how to get your VTH and RTH. Okay, now in continuation, what we can write as, okay, write this as V reference open brackets B0 by 8 plus B1 by 4 plus B2 by 2, where your denominator can be written as 2 raised to 1, which will give you 2, 4 can be written as 2 raised to 2, and 8 can be written as 2 raised to 3. Now, if I have n, we have taken as, we know that n is 3, so this comes out to be as n, this comes out as n minus 1, 3 minus 1 is 2, this is n minus 2, 3 minus 2 is 1. Okay, this one is n minus 2, this 2 is n minus 1, and 3 is actually a n. So the same equation, that is a voltage, effective voltage, V you can rewrite it in this form. Now that network which I have entirely discussed, okay, is going to be given to the circuit over here. Now what is this? This is an op-amp 7.1. Its non-inverting terminal is grounded, okay. Its inverting terminal, what is happening is getting a feedback from the output from the through the resistor RF, and there's a resistor R over here. At this point over here, you're going to give that entire network what we had discussed. So the entire network that we had discussed, you're going to connect over here. So at this point, you're going to get effective voltage VTH and the effective resistance RTH of that network. So that entire network you're going to connect it over here, and then you're going to get the output from the op-amp. The job of the op-amp is only to amplify that voltage which is being given at this point. What is the output of the op-amp? Output voltage is given as, since this op-amp is an inverting mode, the amplification factor is given as RF by R1, okay, which is minus, because it's minus terminal, which is minus RF by R1. R, it's actually minus RF by R. Since it's inverted, you have minus sign, times the voltage that is coming at this point, which I call it as voltage of the R to R network. That will give you my output. So what is happening is, this op-amp circuit is only amplifying that voltage VTH given by that R to R network and giving at the output. So this network over here which I have written, okay, can be rewritten as, okay, if I what now I have to do is, this is the voltage of my network VR to R. So this entire equation has to be substituted over here, okay, and when I substitute, I get my output voltage as minus RF by R, which is the first part, and I have to substitute this Vref. So it comes out to be V0 by 2 raised to n plus V1 raised to 2n minus 1 plus V2 times 2 raised to n minus 2 times Vref. Okay, this is my output voltage, which I can again rewrite as, okay, I'll write the final equation on top. The output is to be given as, what I will do is I will club this term and this term together, and I'll write it as minus Vref. This is V reference, IF times RF by R, okay. Okay, now this inner bracket which is there, if you notice, this is B0, B1, B2, okay, this is N. So this can be written as n minus 0, B1 is n minus 1, B2 is n minus 2. So these constants can be written as B to the base I divided by 2 raised to n minus I, where I will take the values from 0 to, which is the last value, n minus 1. So this is your final formulae. Okay, so what is happening is, this is the voltage that you are going to get at the output of your op-amp, and you are going to give that ladder network that we have already discussed at this particular point, and this op-amp is just going to amplify that output of that ladder network. So this becomes your R to R network or your R to R converter. Whatever I explained up till now, okay, is one type of digital to analog converter. Digital to analog converters, basically what they do is, they convert your digital input to an analog output. Okay, its short form is DAC. It consists of a number of binary inputs and you have a single particular output. The number of binary inputs of the deck will be the power of 2. So 2 raised to, in this case we are taking n is equal to 3. So it will be given to you as 8 possible outputs where you get one output depending upon the input. Decks are of two types, okay, weighted register deck and R2R ladder network deck. So what I have explained to you in the entire video is your R2R ladder network deck. So that covers your first digital to analog converter.